Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. And welcome everyone to the recording of downstreaming processing. I'm recording this class due to the glitch we had last time in our class when it was conducted online. So here are some of the things that we have missed during the class. First of all, as we know, bioprocessing is divided into upstream and downstream stages like we have discussed last time. Upstream covers the preparation and the cultivation of biological materials like fermentation, preparing of the microbes and cell lines in the bioreactors, whereby the downstreaming process begins after the fermentation or the cell culture have been done. So this will include the isolation, purification, and also the formulation. The efficiency of the downstream processing affects the product quality, definitely, the cost, and also the scalability. It stresses how the process integration between the upstream and the downstream improves the overall efficiency of the biomanufacturing. So, as we know, various procedure involve the actual recovery of useful product after the fermentation or any other process together constitute of the downstream process. It's a very important step in the manufacturing because of the different product rely on this, like pharmaceutical industry, such as antibiotics, hormones, and also antibodies, vaccines, enzymes in food industry. So if we look into the definition, as you can see, downstreaming process refers to the recovery and purification of biosynthetic products, particularly the pharmaceuticals from natural source such as animal or plant tissues or fermentation process from microbes, including the recycling of the components and also the proper treatment and disposal of the wastage. If you look at it, it is an essential step in the manufacturing of the pharmaceuticals, such as antibiotics, hormones, and also insulin and human growth hormones, antibodies, vaccines, antibodies, and also enzymes used in the diagnostics, industrial enzymes, and also natural fragrance and flavor compounds. So let's take a look. So let's take a look at this fermentation process. As you can see, after we are done with the fermentation, we are going to have either in situ or ex situ, means that we are going to have either intracellular or extracellular products. So if we have biomass, in this case, we are going to harvest the cells. If we are going to harvest the cells, so the biomass will be a wastage, which means that after we are done with getting what we need, which is the intracellular product, we are going to have a cell disruption. We will see the process later. What are the techniques or the methods that are being used to disrupt the cells? And we are going to have our downstream process following that stage. However, if our product is extracellular, it means that we need the media. So we are going to have a concentration step followed by the purification afterward. So, which means that the downstream process will be different depending on whether our product is actually intracellular or extracellular product. All right. So as you can see here, your downstream process is actually involving many steps, including the mechanical, physical, chemical, and enzymatic methods of disrupting the cells. We have the removal of the insolubles like centrifugation, flocculation, filtration, and sedimentation. We also have isolation that include absorption, evaporation, extraction, and precipitation, and also membrane filtration. We will be discussing a few of those methods. And then we have the purification process, which include the chromatography, precipitation, and also membrane filtration. Finally, finishing, or what we call polishing, it involves crystallization, lyophilization, drying, and also sterilization until we get our final product. So the downstream process is actually depending on several critical criteria or factors that includes product type, protein, for example, metabolites, virus, enzyme, whether or not the product is intracellular or extracellular, and also the target purity level, how pure we need our product to be, and finally the regulatory requirements. Because for pharmaceuticals, for example, you must have a specific purity, and for food, you have another purity level. So that will depend on the product regulatory requirement by the government. The challenges that we face in the downstreaming is that we have low product concentration, a large number of impurities that we have to deal with and remove, and finally the thermolyable byproducts. Some of the products are actually able to sustain at high temperature, but some products will be either inhibited or it will lose its efficiency at high temperature. So these have to be considered during the bioprocessing, downstreaming processing. The downstreaming process is very crucial in determining the success of the bioproducts. It ensures the safety, also purity and efficacy, stability of the final product. So if we look at that also in pharmaceutical, if we have improper purification, that can actually trigger immune reactions or toxicity to the patients. It will also have a reduced activity. So it is also economically significant because it can account for the majority of the production cost, especially when we have a complex biologics like insulin, for example. Um, Regulatory bodies like, for example, FDA, EMA, and in Malaysia we have NPRA, demand the very rigid validation of the steps we take in the purification. For example, from the pharmaceutical industry to illustrate the necessity of the thorough downstream processing. So take for example the GMP, GLP, and also the ICH guidelines. We also have to make sure that we remove impurities like the host cell proteins, DNA like nucleic acids, also endotoxins and residual solvents. So the ideal bioseparation process should combine high throughput with high selectivity and should ensure the stability of the product. Today we are going to look at the major stages in the downstream processing. We have cell disruption only for the intracellular products if the product is intracellular, solid liquid separation, concentration, purification, and finally polishing and formulation. We are not going to have all of those stages or all of those processes, but we are going to look into some examples of the downstream processes. Cell disruption is required when the product is located inside the cells. The techniques include mechanical methods such as high pressure homogenization, when we use pressure differences to rupture the cells. We have bed milling, like agitation of cells with glass or ceramic beds. We have ultrasonication, which applying the high frequency sound waves to break down the cells. We also have the non-mechanical methods, which sometimes use enzyme lysis, like lysozyme, or protease target the cell wall to break down the cells. We have chemical lysis like detergent. Usually we have Triton X100. We have others like ADTA, alkaline treatment. An example is in the E. coli system producing the recombinant insulin. We use high pressure homogenization to release the insulin precursors from the insulin bodies, from the inclusion bodies, from the E. coli. So on this slide, you're going to watch a short video on the disruption of the microalgae cells with the ultrasonication. So please take a look on the video first, and then we are going to continue. So here in this slide, we are going to talk about solid-liquid separation. This is merely to remove the biomass and debris from the fermentation broth. So we have several stages, not stages, techniques. We have centrifugation based on the sedimentation rate differences, density, and also the gravity. So depth filtration, we have this capturing cells within the filter matrix. We have microfiltration. This use membrane with pore size of the 0.1 to 10 micrometer. We'll be explaining this in a short while. An example is the filtration of the fungal biomass in the penicillin production using the rotary drum filter. So as you can see here, this is the rotary drum filter. So let's take a look together. Over here you have the filtration zone, or you can call it the filtration zone, or the drum rotates here, okay, in this section, and the vacuum is applied inside the drum, so this will draw the liquid through the filter cloth. Okay, so these are the filter cloth. And then you have the cake formation zone. If you look at this zone here, this is what we call the cake formation zone. This where the solid will accumulate. So as you can see here, we have the solid accumulation on the outside surface of the drum, where it will form a filter cake. So you have all the solid gathering here. You have the drying zone. You can see the drying zone here, and the drum rotates up the slurry. If you have slurry, the cake is partially will be dewatered by the air suction, okay, in this section. So the air will be sucked to the center. We have the discharge zone. You can see the discharge zone here, okay, where the scraper or blade, okay, is going to having an air jet, where the air jet removes the cake from the drum surface, okay, from here. Then we have a washing zone. That washing zone, or we call it backwashing, that filter the media, the filter media is clean here to remove the residuals and also maintain the porosity of the membrane or the cloth we have over here. So how does this work? The principle of this rotary drum, it will have a continuous rotation. So you can see that we have an arrow here to the rotation. So the rotation acts as a filtering surface. So particularly usually in a large scale, that will be helpful, especially for large particle like a biomass or cell debris. after the fermentation. So this is one of the methods that are used in the fungal biomass because the fungal itself is larger than bacteria. Okay. Okay. So right now let's talk about the centrifugation. Centrifugation is also a mechanical method. It does not use any chemical. It's using a separate component of the mixture here. How do they separate the component? Based on the size. Okay, so take a look at the shape and also the density. By applying high-speed centrifugation force, it is also very important in separating bacteria, for example, or cell debris in the downstream process, even for the DNA. So when the mixture is subjected to the rapid spinning, so as you can see here, this is the centrifuge machine. So we are going to place our tubes inside of the centrifugation machine. This will experience a centrifugal force that moves them outward. Okay, so when you have a denser particle like cells, for example, or spores or cell debris, they are going to move towards the outer edge. So it's sediment faster, and then they are going to be a residual at the bottom of the tube. Lighter particles or liquid remain closer to the center or the supernatant layer. So as you can see here, it will be on the top part of the tube. The separation is faster than natural gravity sedimentation. So this will take shorter time compared to you leaving the tube, for example, outside and then waiting for the sedimentation to happen. This is also using a high speed, like high RPM, so the spin is faster. That's why you have a rapid precipitation. Usually it can reach up to 20,000 for the high speed when we are doing a microbial cell harvesting, while by when we have ultra centrifugation, it could reach up to 50,000 RPM. Okay, so that is suitable for separation of the protein, also virus, and exosome. So what is it helpful for? Centrifugation is usually helping in the cell harvesting, as I mentioned, so your bacteria or biomass will be sedimented, debris removal after the cell disruption, and also separation of the inclusion bodies when we have the recombinant protein production. Another method that we have mentioned just now was the filtration. We have several types of the filtration. We have micro, which is using the micro from 0.1 to 10. We have ultra, which is a smaller size, starting from 0.001 up to 0.1 micron, sorry, and then from 0.001 up to 0.01 micrometer only when it is about nanofiltration. So let's talk about those three because they are very important in the filtration of based on the type of the material that we want to remove. So looking at this one, this is a comparison between those three membrane filtration methods used in the downstreaming process. So looking at the microfiltration, it has the largest pore size. It ranges, as I mentioned, from 0.1 to 10 micrometer. It is ideal to remove the large particle like bacteria, okay, suspended solid, and also yeast. It is also the first line of the filtration. It used the fermentation to clarify the broth before further processing. It doesn't require high energy, so the energy input for this method is low. It is cost effective, but not suitable if you want to have a finer separation. In the ultrafiltration, as we mentioned, it will retain the smaller pores. So we have a smaller pores. It can separate molecules with a smaller molecular weight. So it is suitable for protein, for colloids, and also for viruses. It is also used before chromatography to make sure we reduce the volume and prepare the samples for more processing. In terms of energy, it requires moderate energy, so it is still considered cost effective. The last one is the nanofiltration, which is bridging the gap between those two, and sometimes it could use the reverse osmosis. So in this case, it retains smaller molecules like organic molecules, different divalent ions, and also sugar. It is used for solvent recovery, also for the demineralization and fine purification. But this method requires high pressure, so it requires more energy, and it requires a different type of membrane because you are going to filter a very small molecules. So it will require high energy because you have to apply high pressure. And you need a membrane that could actually sustain in the application of high pressure. So the choice of the membrane here depends on the what we want to remove and what we want to retain. For example, microfiltration is very suitable for clarification. Ultra is suitable for concentration and also purification of the biomolecules, whereby the nanofiltration is suitable for separation involving small organic and also salts. So to choose which one is suitable depends on what are the products that we want to retain or separate at the end of the downstreaming. So another process or another technique used is the concentration. The concentration is in particular to have a bulk, to reduce the bulk volume, because usually we have a very high volume, a large volume after the fermentation. So we are planning to reduce the bulk volume. We have several methods that are used here, like ultrafiltration, which we just mentioned. This will help to retain the macromolecules. We also have reverse osmosis. This also use pressure to force water through the membrane. So this is in order for us to have a smaller molecules passing through the membrane. Evaporation usually uses the thermal methods for heat stable compounds, whereby you can evaporate the solvent and retain your solute. Okay. Precipitation is adding salt. This is one of the methods that are suitable for DNA precipitation or protein as well. So we can add ammonium sulfate precipitation of the serum albumin during plasma fractionation. As you can see here, these are the figures or the explanation of the ultrafiltration, evaporation, applying the heat, precipitation, where you can add salt, high concentration of salt in order for you to precipitate. This depends on what is the molecule that you want to precipitate. For example, in the DNA, we usually add for example, ammonium sulfate. In protein, you can add, we can also add high amount or high concentration of sodium chloride, around 6 molar, for example, in order for us to have a precipitation of the molecules that we want. After that, we can wash out the remaining using a specific buffer. So the reverse osmosis, as we mentioned just now, uses the pressure, so you will force the water in the membrane. Okay, so these are figures showing you the summary of the microfiltration. Usually the microfiltration system will have a pump, it will have a pressure. So wherever that you mean to have the retentate or the tank where you want to collect your permate, okay, or this is the feeding tank. So depending on what is the target, whether you want the larger molecule or the smaller molecule, depending on what is the beaker or the container that you are going to obtain. So this is showing you the number of the molecules that can pass through each of the uh, membrane. For a micro, you will have the macromolecules, whereby when you go down to ultra and nano, you will have a smaller molecule. And finally, the RO or the reverse osmosis will give you the smallest one, like ions and color long molecules weight species. So now we are going to explore the another type of the purification process. Here it is to separate the target molecules from contaminants based on the physiochemical properties. So we have four types that we are going to explain here. Affinity chromatography, specific based on specific binding interaction. Ionic exchange chromatography based on the charge, either positive or negative. Size exclusion chromatography, this is based on the molecular size. And then finally, the hydrophobic interaction based on the hydrophobicity. So if we take a look at the affinity chromatography, the one we can see here, you can see that we have operates principles based on the molecular interaction, like lock and key. So you usually have ligand, okay, and then you have the molecules that are suitable, or would say like have higher affinity, will bind, okay, and then the molecule that is unbound will be exiting the column. In this case, the stationary phase will contain the ligands that are designed to bind selectively to the target molecules. Okay, so the unwanted molecule will be leaving the column. Only the product of the interest will be retained, while all the other impurities will be washed away using the buffer. If we want to elute a certain molecules or certain like unbound molecules, we are going to use different pH. So by playing with the pH or ionic strength, in this case, we are going to be able to elute different molecules or different compounds. This is important in the purification of antibodies. So you can see that antibodies, for example, can be binded to an antigen. So in this case, it can bind, and then the remaining impurities will be washed away using different buffer with different pH. For example, you can use pH 4, pH 5, depending on um, what we are targeting. The next one is easier. So the separation here is going to be based on the net surface charge of the molecules. So if we take a look here, we have the ion exchange chromatography, whereby you will have a stationary phase which will be either negatively charged binding molecule with the opposite charge. So if we have a positive charge stationary phase of the column, then a negatively charged molecule will be binded to it, and on the opposite. So here, if you look, usually we will have resin or any other stationary phase that is going to be um, positively charged or negatively charged. By increasing the salt concentration here or changing the pH, the bound protein are displaced based on their charge density. For example, if you have a protein with a positive charge, so you need to increase or decrease the pH from, for example, 7 to 8 to 9, depending on the molecule itself. Or we can increase the concentration of the salt. For example, from the beginning, we could start with 2 molar and then increasing into 5 molar and then to 6 molar, depending on what we want to elute. So this method is going to be easy to capture and polish the protein of the therapeutic. This is very suitable for the pharmaceutical product, also for the affinity chromatography. The next one here that we have is the size exclusion chromatography. So from the name, this is based on the size. So we have large molecule, medium, and small. So based on the size, the techniques separate molecule based on their size. The column is usually having a porous structure, okay? A smaller molecule enter the pores and take a longer path, meaning it will take longer time to pass through the membrane, whereby the larger one can be coming out faster. So you will have the large molecule. In this case, the large molecule is the one without color. So if the large molecule come out faster because it can pass out faster from the pores. So the minimum interaction between the matrix makes the final polishing steps in buffer exchange easier here. This is commonly used to remove the protein or separating the protein, the peptide molecule, because it is usually using the size of the protein, and protein are usually different in sizes. So it is easier to know that the larger one comes out faster, so you can collect the larger one followed by the medium one and the small one as well, based on the retention time, meaning that based on their interaction with the column. The last one we have is the hydrophobic interaction, where it is based on the hydrophobicity. It could separate protein based on the hydrophobicity. So protein with the hydrophobic region interacts with the hydrophobic ligands under high salt condition. In this case, if the salt concentration is lowered, this interaction will be weak. Okay, so we are going to drop the interaction. When the interaction drops, the protein will elute in order of the increasing hydrophobicity. So it will go or be eluted one by one based on the hydrophobicity. This is very helpful in terms of the precipitation or salt-based concentration steps. Okay, so these are the not in the final purification. So if you take a look at those methods, each one plays a unique role in purification. So you can select based on what you want to achieve in the product purity. The following one that we have is the purification purpose to separate the target molecule from contaminant based on the physicochemical property. We have solid extraction, we have dialysis, aqueous two-phase extraction, and the example is protein A affinity chromatography used to purify the monoclonal antibodies MABS. This is the dialysis process. This is a diagram to show the dialysis process. Usually dialysis process, we have a dialysis bag or tube made from the semi-permeable membrane. This membrane allows the passage of the small molecule, such as salt, but it retains the larger molecule like protein or DNA. So if we look at the bag, the solution we want to purify, it contains both the desired macromolecule and also the unwanted solute in this case. So we are going to put the sample that we want to purify in the dialysis bag. In here, we have a solution of high molarity or high concentration. And then we have another solution. Okay, we have a diffusion solute, and we have a permeable membrane over here. Okay, so if you look at the process here, the bag is submerged in a buffer solution, so you will have the bag in a buffer or uh, salt solution. So due to the concentration gradient between the bag and the membrane, uh, the small solute like urea or ammonia ions or ethanol can diffuse across the membrane into the surrounding buffer. This diffusion will help to continue, or sorry, will keep to continue until we reach what we call equilibrium. So that's the balance, reducing the concentration of the small molecules inside the bag. So this exchange, okay, we can after it is balanced, we can increase the concentration of the solution or of the buffer to make more diffusion happen. This is helpful in terms of removal of small toxic byproducts or purification of the protein. Now let's take a look at some other polishing formulation methods or strategies. This is usually to stabilize, preserve, and also um, prepare the purified product for the storage and for the administration. So we have sterilization, filtration to ensure the microbial sterility. We have diafiltration, buffer exchange and removal of small molecules, similar to dialysis. We have crystallization, which is common in the active pharmaceutical ingredient isolation. Finally, the formulation strategies to make sure that it is the smallest possible. We have lyophilization, spray drying, and also the addition of stabilizers like sugar, surfactant, gelatin, and other molecules. So examples that the formulation of vaccine to be freeze dry or for extended stability, so it will not be inhibited or it won't be inactivated. So this is an example or an illustration of the crystallization process as an example. So we have impure solid. It's going to be dissolved in the selected solvents. The solvent will be selected based on the solubility of that particular solute, and the solution is heated to evaporate most of the solvent. So you have to make sure that the product is basically thermostable. The hot solution then is cooled, resulting in the formation of pure crystal at the bottom of the container. After that, you're going to have a cold solution poured off to obtain the crystal by pressing them between two sheets or filter paper. So this is the simple way. This is how crystals usually look like after the crystallization. This is for different compound. This is suitable for like salicylic acid, for other compounds like also penicillin is purified using this method. So taking insulin as an example, it is usually purified using multi-chromatographical technique. We can use ion exchange and also the HPLC or affinity chromatography to isolate the pure insulin. Okay, so for polishing, the final insulin is usually crystallized or lyophilized into a stable dry form. So to lyophilize, usually we can use either spray drying or we can use the freeze drying. This formulated with the zinc and stabilizer into the injectable solution or the pins for the preparation to be injected. So this is the how it is actually done. The insulin, which is the protein of interest, before being purified, is going to be placed in the column. Okay, so this is the loading process. Then you are going to pour a buffer. So the buffer is going to help you wash out the unspecified protein. In that case, the protein that you want will be binded to the stationary phase. In this case it is resin, so in this case this is what we call ion exchange, and also at the same time affinity. So it's combining two different chromatography in order to obtain the protein of interest, which in our case is insulin. So this is the summary, or this is the some of the process that is being used in the downstreaming process. We have many other processes that are being used in the downstreaming, but we are trying to highlight most of them. So here, if you have any questions about other methods or about these methods that we have summarized here, please feel free to ask if about anything that you are unsure or you do not understand. I hope this is good to cover for the class that we have all faced a technical problem last time. So with that, I think I can close this class, and thank you so much for your listening and for your attention. Assalamu alaikum wa rahmatullahi wa barakatuh.